Hello, it's Dr. Thompson from Taylor University, and I'm going to give you another example of W-substitution. And specifically, this time I want to talk about uh, the idea of what you do when you have a definite integral and you have limits of integration like you do right here. I have the 0 and the 1, and this is the integral of x times the quantity x squared plus 1 all to the ninth. Now, technically, you could take this integral and FOIL everything out with Pascal's triangle and make a really long polynomial and do it by hand, but we don't want to do that. So instead, we're going to think about the fact that we have this composition where we have x squared plus 1 inside the ninth power, and we're going to use the idea of W substitution there, but we want to pay attention to these limits of integration as well. That also matters when you make a substitution. So let's go ahead and use the strategy that we used before. Right now we have this composition here. We have this x squared plus 1 that we would rather be something simple like x. So we're going to make that w. So let's go ahead and do that. So here you can see I made w x squared plus 1. And to do that, I also am going to need to change the differential. I want to integrate with respect to w. So I take the derivative of the substitution. This is an equation itself. And I get dw equals 2x dx. And my whole goal with that move is to solve for dx, which I do by dividing by this 2x. So dx is going to equal dw over 2x. So I'm going to make two changes. I'm going to change x squared plus 1 to w, and I'm going to change dx to dw over 2x. So let's go ahead and make those changes. All right, so now you see I've made those changes, and my integrand looks a lot better. I am almost done, and right here you see I have this x that is going to cancel nicely with this one. That's part of the magic of integration with substitution, that the differential, you're always going to divide by that thing, so you need it to cancel, and if that doesn't happen, this technique probably won't work. Alright, so let's go ahead and do that. You can see here I've canceled the x's, and now just to make everything look a little cleaner, I'm gonna, on the next slide, get rid of the stuff from the bottom, but I also want to talk about these limits of integration, because remember when we started, x was starting at 0 and then x was starting at 1, but now we are using w, not x. Alright, so on this new slide you see our integrand. It's now just w to the ninth dw, and I took the 1/2 outside. However, the 0 and this 1, you have to remember that these were x values. So what I'm going to do is I'm going to change them to w values. I've made an entire substitution. I've swapped out x for w, so I should also swap out those values. So on this slide, you can see I made a little table. If x was 0, then w, which is equal to x squared plus 1, I just plug in x to be 0, and that's going to be 1. And when I make x 1 in that equation, I get 2 for w. Those are going to be my new limits of integration, so let's go ahead and do that. Okay, so I've changed those. I put those in the appropriate spot. Where x used to be 0, now it's 1, and where x used to be 1, it's now 2. And when you look at this equation here, you have an entirely new problem with new limits of integration, and in this case you actually don't switch back, unlike when it's an indefinite integral. The reason for that is that this is a definite integral, so you're only trying to find a number. The answer is numerical. It's not going to be an antiderivative, although you're going to use those to figure it out. So because I have a whole new problem that I really could have just started and done this, what I'm saying is that this problem, this antiderivative, this definite integral, is equivalent to the original one. So if I solve this for whatever number the answer is, that is the correct answer. So I do not need to switch back. The whole point of changing your limits is so that I can do this new problem and get the correct answer. So let's do that. Alright, so here I've done this antiderivative. I left the 1/2 outside. W to the ninth becomes W to the 10 over 10. And then I'm going to go ahead and take the 10 out with the 2 to make it 1/20th. And then I plug in 2 and I plug in 1. Altogether, you get 1023 over 20 in reduced form. Alright, so that is the end of this problem. I have a number. That is the correct answer. I do not need to switch back to x. If you change your limits, you do not switch back. If you do both, you will get the right answer. So let me go ahead and just show you a slide of what it would look like if you had all the work laid out. So you'll have to forgive me, my face is in the way a little bit. But here you can see I have the initial problem. I make my change a variable. I also change my limits. That's the key here. And so when you're done, you'll just get integral from 1 to 2, so those are different, and it's w to the ninth dw, which is, and then the 1/2 comes up front, which is what I have in the corner. The next step is to take that antiderivative like we did, and then you will see the final answer that we got. And so this is what your work would look like on homework if you showed all the steps as one.